Here we are, guys. Welcome back. Sorry for the slight delay here. Things are running a little bit behind in the household this morning, but we are ready to get moving. Today's going to be our second day talking about use of. So today, yesterday the focus was kind of on indefinite integrals and getting comfy with the basic concepts. Today the focus will be on definite integrals and show you lots of examples and try to convince you of a few things that some other well-intentioned but misinformed teachers of mathematics sometimes say, in case you have seen those before. So, here we go. So, we got the credit card going. This is MAC 2311. Section number is OH1, which means we're talking about Calc 1 honors. And the date today is the 24th of November. Today is use of part 2. And this will be our last day talking exclusively about use substitution, although it will show up in the final section, which is section 6.1 that Sarah will be teaching us on our return from the holiday break. Oh, I have some news about the honors class, honors Calc 2. So, announcement. Calc 2 honors in spring, which is course code MAC2312, section OH1. If you've been looking at this for your schedule and stuff, I just want to let you know some things that have changed. It will be Monday, Wednesday, Friday. It will be largely in person, but also taught from what's called a high flex room. What that means is that this room has a bunch of special technology to allow me to broadcast the board through Zoom and to also allow you to interact through Zoom. So this is technically an in-person class, but if you can't make it to the campus or don't want to be in an in-person class for health or whatever reasons, you can Zoom in instead, and it will be a lot like the way we're doing things now. The room has changed from what it was originally posted as, because I just got this from my chair yesterday. So Natasha was saying that she had a schedule conflict, and I wanted to make sure that we could still do this. So let me see what I got. Where did this shit come from? Sometimes changes. Here we go. All right. So the room number is moving to B012. B12 downstairs on the south side of building B. And you can come in person. I will be there in person running the class like a regular in-person class, but the technology in the room will allow us to broadcast the class through Zoom, and it will also allow you to interact with the class through Zoom. So yeah, you can take it as an online class, like technically what we call a hybrid class because it's a live class. But it would be essentially the same thing as this, just instead of seeing my hands on a document camera, you're going to see me in front of a board. And the room has both microphones to pick up what I say and also speakers to pick up what you say. So if you're unable to attend the class in person, you can attend it from home or wherever through Zoom. And yeah, that's the vibe. The other change, the class will run from, it was originally 9:30 to 10:45, but it's been moved to 9:20 through 10:35, back 10 minutes a.m. This is because I have an 11 o'clock class that starts. I have a hybrid online class like the class we're in right now that starts at 11, and 15 minutes is not enough time for me to get my ass home and start that class from my workstation at home. So the class times, I don't know if they've updated this in the scheduling software yet. I've been bugging them to do that. Let's see, hopefully they have. We got OH1. Yeah, they fixed it. All right. So the times in when you look this stuff in Santa Fe, it should be accurate now. B12 is the room, 9:20 a.m. is the starting time. And that is how it should stay. So we've bounced it around a few times trying to find something that works. This is the best thing that we've been able to come up with so far. So if you want to attend the class in person, awesome, do that. If you can't attend the class in person, but you still want to take Calc 2 honors in the spring, awesome, you can do it online. Of course, if you want to take Calc 2 honors, just like getting into Calc 1 honors, I do need to interview you, even though you're here in this class now. It's a formality for the most part. I think anybody who's here would do fine in Calc 2 honors, but I can't permit you into the class without saying I did the interview, so we got to do that. Okay. So I think that's it, announcement-wise. Let's get into the material. So today, we focus on definite integrals via U sub. And the rule there is very similar to the rule for indefinite integrals that we looked at last time. If you're going to integrate from a to b, some function f, where you can think of the inner function as being u of x, and you also have the derivative of that inner function floating around, then you can perform a change of variables to integrate just f of u du, where you think of the variable as just being u. And that's because du is u prime of x dx, like we saw last time when we talked about differentials. The big thing that most people mess up is this: the bounds. You gotta change the bounds. If you integrate f of u du from a to b, that a and b are x values, not u values, but this will be a function of u. So when you perform a u substitution, the big note I have here, when doing u sub in a definite integral, you must change the bounds. And you do not, this is good news, do not go back to the original variable. So the blue notes here are to contrast what you do with an indefinite integral. right? When we did u sub in an indefinite integral, there were no bounds, so we didn't have to worry about changing any bounds. But your answer for an indefinite integral should be a function of the same variable that you started with. Well, here, remember, a definite integral, the output is just a number. And because you are changing the bounds, you do not go back to the original variable. In other words, you just cook up your antiderivative here in terms of the variable u, and you plug in the new bounds, which are u values, not x values. And this is, if you've seen this stuff before, and I know some of you have, if you've seen this stuff before, you may have been told that you don't need to change the bounds, and you should go back to the original variable and plug in those old values to the substituted version. It's just wrong. It's just straight up wrong. Because if you do that, then all of your middle steps are not equal to the thing you started with. So if you want to tell me that the integral you start with is equal to the integral after you make your substitution, you got to change the bounds. And then it is acceptable to go back to the original variable and the original bounds, but it's a terrible waste of time. So I'll show you what I mean. We'll look through some examples. This formula, I think, is fairly opaque. It doesn't really tell us much on its own, at least unless you're already an expert with mathematics and U sub. So examples are for sure the way to go. So, a tame example to begin with. Let's integrate from 0 to pi over 4 the function sine of 2x dx. I am going to draw a picture. And my aim is to convince you that those procedures are necessary. So I'll call this 1, I'll call this -1, I'll call this 2 pi. This is our x-axis. That would put pi around here, pi over 2 around here, and pi over 4 way over here. Sine of 2x is just like sine of x, only it's been scrunched up by a factor of 2 in the horizontal direction. So that means we're going to run through a full cycle just between 0 and pi. And then another full cycle from pi to 2 pi. And I'm integrating only to pi over 4, which is here. So the area that this integral is calculating it's just this area. So this is the graph y equals sine of 2x. Very similar to the examples we saw the other day, the move is to substitute for the inside. And we calculate our differential du, which is going to be 2 dx, because the derivative of 2x is just 2. And then here's how I do this. The work for changing my bounds, I put in the same little box. I write my old bounds, which are x values, x equals 0 and x equals pi over 4. And to figure out the new bounds, I plug the old bounds into this substitution. So when x is equal to 0, u is equal to 2 times 0, which is still 0. And when x is equal to pi over 4, u is equal to 2 times pi over 4, which is pi over 2. So the work in the right half of this box is the work we need to change bounds. Our old bounds were 0 to pi over 4. And our new bounds are 0 to pi over 2. Which means that my integral 0 to pi over 4 sine of 2x dx is equal to the integral from 0 to pi over 2, new bounds, sine of u, 2x is u, that's the substitution I'm making. And then since du is 2 dx, dx is 1/2 du. And let me pop out that 1/2. So I have 1/2 integral 0 to pi over 2 sine of u du. And I will draw the graph of sine u over here. I'll try to keep my scales similar so you can compare the areas. Here is the graph y equals sine of u. And if I'm integrating now from 0 to pi over 2, I get this piece. And just visually trying to draw these on the same scales, you can see that the pencil shaded area here is larger than the pencil shaded area here. We're going out to sort of the same part of the sine curve, that first max. But because this substitution stretches the x-axis by a factor of 2, this piece is twice as wide as it should be. So in order for this area, in order for us to do a computation of this area, which is what this integral represents, and get this area, we need to multiply by 1/2, and that's where the differential is coming. This piece here, remember, is dx, because if you solve this for dx, you get 1/2 du. Also notice if I didn't change my bounds, I would just be integrating up to here, which doesn't have the right shape, right? This is supposed to be sort of that first piece of the sine function all the way out to the max. But if I just went up to pi over 4, that would just be out to here. So that's not even like a scaling issue now, where we would be off by quite a bit if we did this from 0 to pi over 4. So you got to change your bounds. That preserves the shape of the region. And you also need the factor from the differential that preserves the size. From here, this is not hard. This is 1/2 antiderivative for the sine function is negative cosine u. And we do not go back to x's. This is more the beauty of changing your bounds. So first off, if I didn't change the bounds, right, if I wrote this equals this, but with a pi over 4 here, that would be wrong. It would just be a lie. Those things would not be equal to each other. But also, since we changed our bounds, we don't need to plug back in 2x here. We're just going to plug in pi over 2 and 0. So no matter what calculus teachers have told you in the past, you do need to change your bounds. And in a definite integral, you do not need to go back to the original variable. The cosine of pi over 2 is 0. So this is 0 minus negative cos of 0. Well, cos of 0 is 1. That's minus negative 1 or plus 1. So this is just 1/2. There's nothing too hard here. Again, when you're doing a u substitution in an indefinite integral, all you have to worry about is the differential. And then remember to write your plus c, remember to plug back in for u at the end. When you're doing u substitution in a definite integral, remember to change your bounds. And remember that you do not plug back in 2x ever. You just evaluate this thing from these new bounds. It's nice. And of course, with definite integrals, we don't write a plus c. There's no plus c. All right, any questions on this fella? It is, I agree, very tidy. Mathematicians are fond of tidy. Okay, then let's try another. I want to integrate from 3 to 5 the function 1 over x minus 2. Again, I'll draw the picture here. You don't need to draw this picture every time, but while I'm trying to convince you of these things, I want to. Here's 1, here's 2. This function has a vertical asymptote at x equals 2 because the bottom is 0 there. And it looks like this over here. There's another branch over here, which I'm not terribly worried about because I'm working from 3 to 5. So the area I'm computing here is this area. This is my x-axis, and this is the graph. I equals 1 over x minus 2. What would I substitute for here?
X minus 2.
Very good. So I'll make the substitution u equals x minus 2. What is du?
1.
Yeah, just 1 dx, right? Du dx would be 1. So du is 1 times dx, or just dx. I'll change my bounds. Write down the old bounds here, x equals 3, x equals 5. When x is equal to 3, u is 3 minus 2, which is 1. And when x is equal to 5, u is 5 minus 2, which is 3. So my integral from 3 to 5, 1 over x minus 2 dx, is going to become integral 1 to 3, 1 over u. And here du and dx are equal. There's nothing to solve for or plug in or cancel. In other words, this change of variables doesn't stretch the x-axis at all or compress it. It doesn't do anything to the x-axis. This is just a shift. And if I sketch this function 1 over u along the yu axis, this is the u-axis. What that change of variables does is it just slides everything over to back to the left. This is the graph y equals 1 over u. And you'll see that the area here from 1 to 3 is the same as the area in the original from 3 to 5. Right? And there is no scaling factor here. There's no 1/2 out front like the last problem because there's no stretching going on here. We're just shifting things over. Now, the reason we make the substitution in the first place is because I don't have a rule for the antiderivative of 1 over x minus 2, but I do have a rule for the antiderivative of 1 over u. What is an antiderivative for 1 over u?
ln absolute value u.
Very good. And I don't write a plus c because it's a definite integral. I don't plug back in x minus 2 for u. I just evaluate this antiderivative between these new bounds. Nice and clean. So this is the natural log of 3 minus the natural log of 1. I'm not writing the absolute values because 3 and 1 are both positive numbers. The absolute value of a positive number is just that number. Also, the natural log of 1 is 0. So this is just the natural log of 3. And you can think of it either way. It's the area under 1 over x minus 2 from 3 to 5. It's also the area under 1 over u from 1 to 3. It's the same thing. Not too bad, right?
I have a question. Will it show the 1 to 3, the 3 if minus 3 is, say I just write logarithm 3, absolute 3.
Let me make sure I
Will
understand.
it happen this situation?
Help me out. Could you just repeat that for me one more time?
Will it happen this situation logarithm absolute u from minus 1 to minus 3, and I just write logarithm absolute minus 3 minus logarithm absolute minus 1, this situation in the exam or exercise, anything?
Yeah, so if
Anyway.
we wanted to integrate from like -3 to -1 over u du, we could do that. And this would come out to the ln of the absolute value of u from -3 to -1. And that would be the ln of the absolute value of -1 minus the ln of the absolute value of -3. And then I would make them separate steps here. So then we'd say, okay, the absolute value of -1 is 1, and the absolute value of -3 is 3. And so this would be 0 minus the natural log of 3, just negative ln of 3. Yeah, something like this certainly could show up, and these would be the steps I would want to see there. And kind of the signed area being measured there is the stuff over here from -3 to -1. But yeah, it works just fine. But I do think it's wise to write separate steps for this and this. That way here we can see. If you did just jump to this, I wouldn't take points off. But I think for clarity, it is nice there. Here, I suppose I it's not a bad thing to say we should write absolute values here, and then you could do this in a separate step. But because these numbers are positive, I feel like it's a little redundant. Because these numbers are negative, we do want to make sure our reader understands that it's the absolute value that changes them. But either one would be okay, really. If you went straight from here to here, I would not take points off. I would consider that acceptable. But it is, I think, nice to have this line.
Thank you.
Sure, of course. Okay, let's try something a little more complicated. Let's see. I have examples in my brain that I like a lot, but let me make sure I'm not missing anything of the flavor the book really likes. I don't want to be leaving anything out. Yeah, we haven't done much trig stuff, at least not challenging trig stuff. We can do something like that, but a definite integral would be nice. Let's look at number 57. So the integral from 0 to pi over 6 of sine t over cos squared t. This is one of those integrals that you could actually do a number of different ways. You could try rewriting this as secant times tangent. It is that, right? 1 over cosine is secant, sine over cosine is tangent. And you can get there without substitution. But since we're practicing substitution, does anybody see a substitution we could make here?
I was making the u is equal to cosine
Very good.
t.
Yeah. If u is cos t, then this piece down here would just be u squared. And the reason this is nice is because upstairs I have a sine t, and the differential here would be negative sine t dt. I also will change my bounds when when x is not x, when t is equal to 0, u will be the cosine of 0, which is 1. And when t is equal to pi over 6, u would be the cosine of pi over 6, which is the square root of 3 over 2. Now, this would mean that 1 over negative 1 over sine t du is equal to dt. So when you go plugging in this substitution, you'll have integral 1 to the square root of 3 over 2. I'll write it out. Sine t over u squared times negative 1 over sine t du. And the sine t's cancel. This way of thinking about things is all right, but it's not very sophisticated. And I'll show you as we move through more problems, a kind of better way of thinking about it. This negative, I'll bring out of the integral. And I have 1 to root 3 over 2, 1 over u squared du. We could soak this negative back in by flipping the bounds over, but I'll just leave it for now. We don't need to do that. 1 over u squared is u to the negative 2. And an antiderivative there. We add 1 to the power, so that becomes u to the negative 1. And we divide by that new power, but dividing by negative 1 is the same as multiplying by negative 1. And this negative can come out. So this is just u to the -1, or 1 over u, evaluated between bounds 1 and the square root of 3 over 2. And I'll continue up here. So kind of one of the nice tricks is that the evaluation brackets are also a linear operator, meaning if I had a 2 here, I could pop the 2 out. If I have a negative here, I can pop the negative out. If I have a sum of 2 functions in here, I can evaluate each of them separately. In any case, what we get here is 1 divided by root 3 over 2 minus 1 divided by 1, which is 2 over the square root of 3 minus 1. And that's the end of the story. If you'd rewritten this as secant times tangent, your antiderivative would have been secant. And secant is the same as 1 over cosine. So it's nothing crazy here. You can do it either way. The other little thing I kind of wanted to show you is an alternate way of handling the differential. The fact that here du was negative sine of t dt. So your original integral 0 to pi over 6 sine t over cos squared t dt can be rewritten as integral 0 to pi over 6 1 over cos squared t times sine t dt. And what you would notice at this stage is that this piece is negative du. So rather than like plugging in and canceling, because remember, mixing variables in an integral is bad. Having like t's and u's in here is a bad thing. We really don't like that. Remember what we said, we can't do any integration until everything is written in terms of the new variable. That's all important. It's nice to avoid ever doing this. It's nice to avoid ever writing an integral that has both the old variable and the new variable in it. So if you can split up your integrand into pieces that you know would cancel or go away or be soaked up by the differential and other stuff, then you can avoid that step. And I can say, okay, this is now going to be the integral from 1 to root 3 over 2, 1 over u squared times negative du. And that gets us to the same place, right? Negative integral 1 root 3 over 2, 1 over u squared du. But we never have to write that step where I've got u's and t's both in the problem at once. Let's try a new problem and let's attack it kind of in this way. Let's see if they've got anything else in here that I like. Sure. How about the integral from 0 to 1 of e to the z plus 1 divided by e to the z plus z dz. Pro tip, always cross your z's. Otherwise they look like 2's.
U is equal to e to the z plus z.
Very good. But before I make that substitution, thinking ahead that that's the substitution I'm going to want to make, I'll rewrite this as integral 0 to 1 over e to the z plus z times e to the z plus 1 dz. And now when I write that substitution, e to the z plus z, I calculate du, which is derivative of e to the z is e to the z, derivative of z is 1. So du is e to the z plus 1 dz. That's exactly what I have here. Also, we'll change the bounds. When z is equal to 0, u would be e to the 0 plus 0, which is 1. And when z is equal to 1, u would be e to the 1 plus 1, which is e plus 1. And the nice thing about having written this in this fashion already is that I see this is du. So I never have to have that step where my variables are mixed. I now just integrate from 1 to e plus 1. This piece is 1 over u, and this piece is du. So that's going to be another natural log. This will be the ln of the absolute value of u, evaluated from 1 to e plus 1, which is the natural log of, again, these are positive quantities. And again, the natural log of 1 is 0. So I just get the natural log of e plus 1. So when I personally do u substitution, I always do it like this. I always look around in here for the piece that's going to be used up by my differential. So I think about the substitution I want to make. I think about its derivative, and I look for that piece in my integral. I try to take that piece and write it over here with the original differential so that I can just say, all right, this whole thing is going to be replaced by du. And that allows me to jump straight to this without any canceling or mixing variables, which is nice. Another place this shows up a lot is in integrals of trig functions. Something like this. Where I would substitute u equals cos theta.
Is that a 2 or 5 above the cosine?
5.
Oh, okay, cool.
Sine theta, d theta. Because I can immediately recognize this as negative du. Again, when theta is 0, u is 1. And when theta is pi over 2, u would be 0. Cosine of pi over 2 is 0. So this integral would become integral 1 to 0. Cos to the 5 is u to the 5. Sine theta d theta is negative du, so I can pop out the negative and just write the du. And this is an instance where I would flip the bounds over. Negative integral 1 to 0 is integral 0 to 1. And then that fella is 1/6 u to the 6, evaluated from 0 to 1, which is just 1/6. U substitution with definite integrals, it's not any harder. And in fact, I think in some ways it's nicer because you can kind of rationalize a lot of the steps a little bit more by thinking about what happens to the coordinate axes under those transformations. I think I may let you guys go a little bit early today because we really don't have enough material for a full day's lecture here, but I want to look at just one or two more. I want to spoil that one for you. That's going to be in your homework. Let's look at 59. I forget, is that a negative? Might be. Nope, just this. Okay. What could I try to substitute for here?
U is equal to 1 over x.
Very good. And kind of the thinking there is if u is 1 over x, then du, the derivative of 1 over x, is negative 1 over x squared. So du would be negative 1 over x squared dx. And while I'm here, let me go ahead and change my bounds. When x is 1, u would be 1 over 1, which is still 1. When x is 2, u would be 1 over 2, or 1/2. I can, before I plug into my substitution, rewrite this as integral 1 to 2 e to the 1 over x times 1 over x squared dx. And you see the 1 over x squared, again, negative du. So this will be negative integral 1 to 1/2 e to the u du. And again, this is a place where swapping those bounds, flipping the bounds over and soaking the negative up is nice. Integral 1/2 to 1 e to the u du, which would be e to the u from 1/2 to 1, or e to the 1 minus e to the 1/2. So this is a skill we need to become proficient at. Certainly there will be u substitution problems in section 6.1 when we're finding areas between curves, which Sarah is going to teach us after we get back from break. And there will be u substitution problems in their own right on the final. More important though, at the start of Calc 2, you'll be worrying all about integration methods. And this u substitution is sort of the fundamental integration method beyond just knowing your basic antiderivatives, the stuff from that table. So you need to know your basic antiderivatives for sure. But the next most important thing is getting good with u substitution. You're going to learn a lot of different methods in Calc 2 for evaluating integrals and antiderivatives. But many of them, as sophisticated as they are, will reduce down to a u sub problem. So maybe you do some integration by parts or some other sneaky technique that you'll learn in Calc 2. But then after that, you still have to do u sub to finish the problem. So this is something that's going to stick with us for a very, very long time. See if there's anything else here that's really worth doing. Yeah, maybe just two more problems in parting here. Quick, simple stuff. This should scare you. It scares me. Any thoughts?
We could use symmetry.
Mm-hmm. Yeah, we cannot do a substitution here. There's nothing really nice to substitute for. No substitution I could make will get rid of this. No substitution I make will get rid of this. And any substitution that involves this is not going to play nice with this. Any substitution that involves this is not going to play nice with this. But what symmetry can we use?
It could just be the integral of 0 to pi over 3. Well, 2 times the integral of 0 to pi over 3 of this.
That would be true if this was an even function. X to the 4 is even. What about sine of x?
It's odd.
Yeah, sine x is an odd function. So what is this whole function? X to the 4 times sine of x.
It's odd.
Yeah, this is an odd function. In general, if you multiply an even function by an odd function, you will get an odd function. We can check. F of negative x would be negative x to the 4 times the sine of negative x. Negative x to the 4 is just x to the 4. Sine of negative x is negative sine of x because sine is odd. And then that negative, you multiply positive times a negative, you get negative x to the 4 sine of x. And this is negative f of x. So yeah, f here is an odd function. Therefore, what is true?
So it's equal to 0.
Very good. All right, if we integrate an odd function from negative a to a, as long as that odd function is continuous, you'll always get 0. So here we're not going to compute this. And in fact, finding an antiderivative for this is beyond us at the moment. This would require something called integration by parts. 4 runs of integration by parts. It's a nasty antiderivative. But using the symmetry argument, we can say that this integral must be 0 without ever computing it. All right. I do think this is a good place to stop for today. There are a handful of other problems in here that exploit symmetry arguments like this one. This is the one we just did. Are there any others in here? That looks like it. But I encourage you to look for symmetry arguments everywhere you can. And yeah, I think this is probably where we will leave it. Definitely, I can
File
put
sticker.
problems related to symmetry on the test. Yeah. Yes, go ahead.
So it took me a while to figure out what was happening because I did the homework already, but I hadn't used like the changing the bounds and I had just done it. And so what I had done is like I took the integral and then I put the u back into the equation and then I solved it using that, like the original bounds.
Mhm.
Is that right? Or because the answers were right. And
Yeah. So fair question.
is that like the
This
same
comes
thing?
back to what I was saying at the start. So I've been trying to avoid this, but you can arrive at the right answer this way. But let me show you a quick example. So if we're looking at the integral from 0 to pi over 4 of sine of 2x, that one that we did, and you make the substitution u equals 2x, du equals 2 dx, and you write this as 1/2 integral sine u from 0 to pi over 4 du. I contend that even though this is well-intentioned, it's not correct. And let me show you why. Actually, what I should do here is put a question mark. It's true that if you calculate your antiderivative here, then plug back into x, then use the original bound, you will get the right answer. But are these things equal? So the first one, integral 0 to pi over 4 sine 2x dx, that comes out to 1/2, right? And that's what we saw by doing it as we did. If you integrate sine u from 0 to pi over 4, you get 1 minus 1 over root 2, which is not 1/2. So here's what you could say. These are not equal. But if you say, okay, to do this integral instead, consider the indefinite integral sine 2x dx, which is equal to 1/2 indefinite integral sine u du, which is 1/2 times negative cos u plus c, which is negative 1/2 cos 2x plus c. Therefore, integral 0 to pi over 4 sine 2x dx is equal to negative 1/2 cos 2x evaluated between those original bounds. And from here, you will get the correct answer. But the thing is, if you make this substitution and you tell me that the original integral is equal to the new variable integral, but with the old bounds, that's not correct. So this guy and this guy are different. And that's why I harp so hard on changing the bounds. We want to say the thing we started with is equal to the next step, is equal to the next step, is equal to the answer. And if you're going to avoid changing the bounds and you want to go back to the original variable, you can do that, but you kind of need to say, all right, in order to solve this integral, I'm going to step aside and work the indefinite integral instead, then take my core antiderivative from that and evaluate between the original bounds. I think that this is more work, and it's all to avoid something that is actually really nice and has a good, solid geometric meaning. So, like if we want to be understanding, where did those pictures go? We want to be understanding what's going on with U substitution, I really feel we should change the bounds. And what I tell people in my Calc 2 class is that I will take off points if you do not. So think about this example, right? I want to be able to compare those areas. I want to be able to think of both of these as definite integrals rather than saying every time I'm going to do U sub, I need to run off into indefinite integral land and then come back. So really, this integral is actually equal to this integral. These guys are straight up equal to each other. So if you want to perform the U substitution on the original integral, which is a definite integral, and say that that is equal to another definite integral with the change of variables, then you do need to change the bounds. In Calc 1, as a general rule, I don't take off points if you do things as you've described. In Calc 2, I do. And I think in Honors Calc 1, I have an obligation to push you towards the thing that is true. So while there's nothing epistemologically wrong with what you've done. You got the right answers, as long as you understand that what you're really doing is kind of coming off in a separate step and computing an antiderivative and then going back to the original problem. The workflow is so much cleaner if you change the bounds, and the geometry makes sense. I can compare this area under the original function to this area under the modified function. That understanding is important enough that I will ask you on the test to please change bounds. When you're doing a definite integral by substitution, please do change the bounds. Do you need to go back and rework every homework problem? No, probably not. Would I go back and rework one or two of them to make sure you're comfy with this procedure? Yeah, probably.
So is it the sine cosine if the U substitution is in the sine and the cosine, those solid cannot change the bound. But if U is equal to equations, that could change a bound.
I'm not sure I understand. So even if you're substituting for something like sine or cosine, we certainly can still change our bounds like we did here, right? Our original bounds were from 0 to pi over 6. And when we made that substitution, we changed them to 1 and root 3 over 2, like this. Maybe I'm not understanding the question.
That's fine, thanks.
Okay. I have one more thing to argue this with here. And let me see if I've put it in your modules. I always put it in my Calc 2 modules because I have to argue this to a bunch of them at the start. No. So here, let me share with you a page that I make my Calc 2 students read at the start of the semester to explain why I require them to change the bounds. Why we always change bounds and substituting a definite integral. So this, it took me a long time to find any website that actually talks about this in a good way. This website breaks down the mechanics of U substitution in a really nice fashion. So if you want to find the area under the red curve from 0 to 0.5, that's the same as the area under the blue curve from 1 to 1.5. And that's sort of the way we think about this. And then they do also describe the scaling factor that we talked about here, right? Like stretching out the axis and stretching it out maybe different amounts at different places. So if you want to kind of revisit that concept, I'll paste this in the chat. There's one other big reason, and before I let you go, let me share this. In Calc 3, you're going to be looking at integrating over regions. Let's say double integrals. Instead of integrating over an interval, right, like from 0 to 1, you'll be integrating over a two-dimensional region. And when you make a change of variables in an integral like that, the region will not only, it's not just the case that your variables change, your region will change shape. And you need to understand why we're doing that when you get to this part of Calc 3. So this task, which I know right now looks like a bunch of random gibberish, will make so much more sense if you get into the habit of changing your bounds when you do a regular definite integral in Calc 1 and Calc 2. So you see here, the original region we're integrating over is the tan region here. And we think of ourselves as integrating from left to right. And when we make the change of variables, we're going to think about that as integrating from bottom to top. This sort of geometric intuition, here's another one. We're going to make a change of variables, and instead of integrating over the domain here, which is gray, in our new integral, we'll be integrating over this domain, which they call d prime in gray. Being able to understand what's going on in Calc 3 here will be made so much easier if you get into the habit of changing your bounds here. And I think the best best example we have of something like that so far is this, where you've got this region from 3 to 5, and that interval, that's the region we're integrating over. When you make this substitution, becomes this region, the interval from 1 to 3. So the substitution changes the domain of integration. And that is an important concept. So like I said, in a normal Calc 1 class, I would not take off points for doing problems as you described, as long as you're careful about it. As long as you step aside, do the indefinite integral, then come back and evaluate between the bounds. But because this is an honors class, and because certainly in Calc 2, it will be a necessary thing, I am going to ask you on exams to please change the bounds. So it's okay if you did some problems like that. Not going to hurt you, but you do want to practice this other way of doing things because it is genuinely superior. It is genuinely the correct way to do things. And we cannot write equalities like this down if we use the old bounds. If I was to still have this as integral 3 to 5, that would just be wrong. It would be a lie because that would be the natural log of 5 minus the natural log of 3, whereas this is the natural log of 3. So I get it. And I know that this is a frustration because it's back on sympathetic face. I know that this is a frustration because it's a way of approaching problems that allows you to get the right answer. And it feels like as long as I'm getting the right answer, everything should be fine. But there is more to mathematics than that. And I hope that that's one thing that we've kind of gotten a little feel about through the semester is that it's not just the result that matters, it's kind of the mechanics. Why? Why does that give the right answer? Why does this give the right answer? And what could be different about the two? And the big difference here is that the in-between steps won't be equal to the original thing unless you change the bounds. So in order to be like logically consistent, I'll request that you get in the habit of changing bounds. All right, I am going to go ahead and close out the class here. Like I said, don't go back and rework the whole homework set. If you've solved all those problems and you've gotten all them right, just go back and work 1 or 2 and make sure you're comfy with how to change the bounds and make sure you understand kind of what's going on here when we do that, that we really are moving this region over. And sometimes we're changing the shape of the region. Sometimes it's more dramatic than that. And that in later classes, when you're doing iterated or multiple integrals, having practiced this now will make understanding that a lot easier. All right, gang, I gotta run. Office hours today, 1 to 2. I hope you guys have a lovely and safe Thanksgiving break. I'm not going to pile you up with any extra stuff over that break, but when we come back on Monday of next week, Sarah is going to teach us how to find the area between 2 curves, which is a whole nother fun thing, but not too big a stretch from where we are now. That's it.
Is this chapter 6.1?
6.1 is the next section. Yeah.
I completed the outline for that lesson. Is it all right if I email it to you today?
Sure, please. Yeah, thank you.
Okay, sure.
All right, gang. Take care.